Oh, yeah. No, 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 no. Oh, there it is. All right, so what I want to do, we were just talking about e to the x. Okay, now here is a graph of e to the x. What I would like us to do is I would like us to look at the first degree polynomial of the Taylor expansion of e to the x. 1 second. What does that mean? I forgot to go over that. If they ask for let's make a part C. Oh, let's make a part D. Let's say they ask for the nth degree Maclaurin or Taylor, it doesn't matter, polynomial of f of x equal to e to the x. Now, in this situation, I can have the first degree, second degree, third degree, fourth degree. Let's say in this situation, I want my n to be equal to 3. So, what are we asking for? We're asking for the third degree Maclaurin or Taylor polynomial, where I should say in this situation we have x equal to 0, or a is equal to 0. I want that expansion. What is that? That would be then 1 plus x plus 1/2 x squared plus 1/6 x cubed. And we would stop there. Polynomial will have a finite number of terms. If I say series, then that is an infinite number of terms, ... But if I want a third degree polynomial, I will go all the way up to my term that has x to the third power. Sometimes they might go by increments of 2, like it'll be 0, x squared, x to the 4th, x to the 6th, and so on and so forth. So if they ask for the third degree, we're not going to have it. If they ask for the fourth degree, then it would be this term right here. So it varies, okay? But if they say the third degree polynomial, then you want to make sure you end up when x is actually to the third power. Okay? Now, how can we use this? If we look at this graph of e to the x, there's a graph of e to the x. If I do the first degree Taylor expansion at x equal to 0 of e to the x, the first degree is just 1 plus x, if you look at that. And if you look at this looks exactly like the tangent line. Tangent at x equal to 0. Why is that? Why is that? That is because if you go back to your Taylor series, the first degree when x is to the first power is this. What does that look like? Equation of the tangent line. This right here is the equation of the tangent line. And what do we use that for? We use that to do some sort of linear approximation, right? So when I go back to my graph, we would use this and we can do some linear approximation. It looks like it's good from here to about here, whatever that small interval is. Let's say I do the second degree expansion of e to the x. So I'll do 1 plus x plus, what was it? 1/2 x squared, 0.5 x squared. That is this. Now, if I look at that, look at how close it is. Here's my point of tangency. And look at how close it is to approximate. It's a larger interval where I can actually approximate my curve, right? Then, if I were to do the third degree, 1 plus x plus, okay, plus, what is the third degree? 1/6. Oh, yay. 1 divided by 6. Okay. Then you see this cubic function. Now it's really close to the curve from here to here. And the more terms you add, the longer it's going to be a better approximation of this actual curve. And so each time that interval is going to get larger and larger and larger. But what happens when we have an infinite number of terms? It should be then that curve, right? So if I look at this, when I did this expansion, for e to the x, since I had an infinite number of terms, that means that this is actually equal to e to the x. But if I were to do a polynomial, I can use this polynomial to approximate my e to the x, right? So then that means that this is approximately e to the x, which is equal to f of x. That would be my notation, because we are using this to actually approximate, okay? And if you think about it, when we enter things in our calculators, for instance, let's get a calculator out. If I enter things in my calculator if I said something like cosine of, give me a number. 85, like so. It gives me this. It does not give this to me because the calculator's got every single point on the unit circle, which there is an infinite number of degrees on the unit circle, right? And it has it memorized to this many decimal places. What does it actually do? It has a Taylor polynomial in there where it runs that program and it does this equation for every single x equal to a, whatever one I want to approximate at. And it will generate to this degree of decimal accuracy, whatever decimal I want. But it does not have every single one memorized. It just uses an approximation of whatever function I have. Okay? So, now that we know that it's an approximation, let's do a problem. Oh, not that problem. Okay? Which problem? These problems. Oh, okay. Okay, so let's do a problem, one of these problems. So if I do number 9 like this, if I do something like number 9, actually, if I do number 9, what does this say? This says a function has derivatives of all orders, x equal to 0. And we're going to let Pn, so this is, what does this mean? This is the nth degree Taylor polynomial about, and it'll tell us about this. So the minute that they say this is the same thing as the Maclaurin. But remember, Maclaurin is just a Taylor polynomial, okay? It is known that f of 0 is equal to 8. The first degree polynomial evaluated at 3 is equal to 5. The second degree polynomial evaluated at 3 is equal to negative 11. Find this. All right. So I have this. Okay, so I don't know what my f of x is, but I do know that I've got